And we are back. So today we're going to switch gears in a matter of sorts, and we're going to talk about support vector machines. I don't expect to get through all of this module today. We'll certainly carry on the balance of today that's left on our Tuesday class meeting, and perhaps even if need be on next week Thursday's class meeting. So let me start. Let me just set the pen at the outset. How about blue? Why don't we begin? So when we last left off, we talked about validation as a means of doing model selection. And in that, we had a number of different learning models, H1, H2, up to and including H big M. So we had M many models. And we took our original in-sample data, D here, script D, and we partitioned it into dtrain, and we set aside our validation set, dval, which was of size big K. And as such, dtrain had n minus k examples. And because we took this validation set out of the n minus k, there's this natural tension between this training error and this validation error. Nonetheless, this validation set, because your training does not use them, your models will not have seen them when they were training, all of the data points in this validation set act like out-of-sample points. And therefore, once we have a final best hypothesis as a result of training each one of these M many models on dtrain, we can evaluate the validation set and use it as a proxy, an estimate, as it were, of out-of-sample error. So here, the result of training on dtrain, we have a limited final best hypothesis, and we noted that with this minus sign. So here, G1 minus is the limited final best hypothesis for the first model, training on dtrain. Likewise, G2 minus is the limited final best hypothesis as a result of training the second model, H2, script H2 on dtrain, and so forth. And so then when we use our validation set, we pick the best limited final best hypothesis, which we called last time GM minus, GM star minus, that is associated, so we pick the GM star minus that's associated with the best performance out of sample, and that would mean the smallest validation error. And again, that validation error, E1, is the validation error for H1, our limited final best hypothesis for H1, G1 minus, and EM is the error estimate for out-of-sample performance for this limited final best hypothesis, GM minus. And so we have an optimistic bias because we're picking, and when we pick that best model, we then combine back the validation set with the training set, form the full training set, which has more examples, and then use that winning model to train with a full data set. And Hoeffding's inequality and the VC dimension tells us that out-of-sample error will improve. So with this, we saw that there's a tension here between dval and dtrain. The bigger dval is, the better your out-of-sample error estimate, E1, E2, up through including EM. But the problem is if dval is too large, you're robbing your training set, so your limited final best hypotheses are going to be poor. And in that regard, your estimate for out-of-sample performance, while it gets better and better and better, you're going to have a better out-of-sample performance estimate of something that has very poor error. In the other direction, if dval is small, well, good news, dtrain has a lot more examples, and therefore each one of these limited final best hypotheses is going to be better performing because Hoeffding's inequality and VC dimensions tells us, VC bound tells us, if you have more inputs to train on, your out-of-sample error performance is better. But because dval is small, your error estimate out of sample is poor, and therefore you're going to make a bad decision when you're picking from among these hypotheses which one is the best. Okay, so we talked about that last time, and we're able to strike a balance between K, the validation set size being large, and the need to be small at the same time using cross-validation. And so in that, we leave one out, and that's the way you make your training set as large as possible, and then you average over each one of those singleton training sets that consist of just a single data point And so here I have a singleton validation set, and that singleton validation set is going to be different depending on which version of the training data, dtrain, that you construct. So we'd have a singleton validation set consisting of the first data point, consisting of the second, third, fourth, up to including the nth. And so we're going to take the average out of sample error estimate, albeit singleton, and that's going to involve all of these n data points, thus making this validation set k as large as possible. And so using cross-validation error, now we take that as the criteria that we use to select that GM star minus, which was the best of the limited final best hypotheses, and we call that validation error. Okay, so let's switch gears and talk about this idea of a so-called maximum margin classifier. And so the idea of maximum margin is, of course, we have a linear hypothesis, and there are many choices we can have for this linear hypothesis. And the question we ask is, which one is best? Now, if you look here, we have this purple. That purple is our linear hypothesis, okay? So that's our H of X, or our W, if you will. Now, we're going to also introduce some new terminology. Here, on either side of this hypothesis, H of X, we have some data point, regardless of if it's a negatively classified point, a negative example, or a positive point, positively classified. We have some point that's closest to the hypothesis, closest to this linear model. Now, the distance between that closest point to the linear model, that's called the margin. And so that margin here is between the hypothesis and this red point, that negative example is closest to the linear model, the hypothesis. And therefore, the margin we draw on both sides would be that minimum distance to the closest point on both sides of the hyperplane, on the negative side and the positive side. We could consequently also have had a blue point. Let's say if we had a blue point here, which was even closer, right? The margin would be even smaller, the same size in both sides of the line. So the margin is the distance between the closest point and the hyperplane. And in finding your linear hypothesis, certainly there are many choices you can make for which hypothesis you choose. But if we look at this example, sort of intuitively, we see that if you can shatter this data set, where we have here the negative outputs for your hypothesis and the positive outputs, right, the positive side of the line and the negative side of the line, this is the same dichotomy. So we have red, red on top, blue, blue on bottom, red, red, blue, blue, red, red, blue, blue. Now, if the same looks like the same hypothesis as far as its behavior in generating this particular dichotomy, but if we look at it and we had a choice between this first hypothesis, the second hypothesis in the center, and this third hypothesis on the right, intuitively, you'd want to choose this third hypothesis. And why is this? Well, because if you look at it, well, there's this larger gap, a larger margin between the data points on the positive side classified by this hypothesis and the negative side. So why is this idea of bigger margin better, right? Why is it better? Now, if you think about it intuitively, if you have some data points, let's take, for example, this red data point. In fact, I should probably set this pen, set it to red. Now let's take a red data point. What happens if we add noise to this point? Well, that point could move up here. I'll kind of draw an empty version of it. Or with noise, that point could move over here. Well, if we add noise to that point, we're going to move its position in feature space. And you'll notice with a smaller margin, if we move this point, we're more likely to misclassify because of the smaller margin, like this example. If we just move it this amount, now all of a sudden that point is misclassified. It's a classification error. Whereas with this version of the hypothesis, the linear hyperplane, if we move that point the same amount, well, we still produce the correct classification. And moreover, we'd have to perturb this point far more in order for this to become a misclassified point. And so certainly there's this idea with larger margin of robustness. And moreover, if you have a lot of examples of a point, say different variations of it, right, they all maintain the correct classification as a consequence of this larger margin. So this idea of a larger margin is better because this adds this sense of robustness to your classification. So now the question then is not just selecting any hyperplane, any linear hypothesis, to select a linear hypothesis that also is a maximizer of the margin, the so-called max margin linear hypothesis. So let's recall some conversation and discussion we've had about growth functions. And we said a growth function is the count of the number of dichotomies that a function class can generate. Now here we have 3 data points, and we'll list all the different or a number of dichotomies that we can produce. So if we do that, of course, we have this dichotomy, right? All the points blue. We have this dichotomy, 1 red down below, 2 blue. This dichotomy, going left to right, we have all red, that dichotomy, 2 red up here, blue, and so forth. And so these are all the possible dichotomies that you can generate, all 8 of them, using a line in the plane, given a data set of size 3. Okay, so now if we took into consideration not only just the hyperplane, but also the margin, we want a large margin, as large as we can get it, well, now we're ruling out some of these choices for the hypothesis that we can consider. So let's take, for example, this dichotomy, and we'll look at the dichotomy that we get when we try to maximize the margin. Okay, so here for this dichotomy, we see a margin that's very close to the points. It's not doing too well because they're very close. Okay, well here for this dichotomy, right, we see a larger margin. Here for this dichotomy, it's about medium size. Here it's not very good because these points don't have to move very far to go across the hypothesis and be misclassified. And so if we were to put a constraint that says have a minimum size margin associated with the hypothesis, we'd effectively prune away some of these choices of hypotheses that we can have associated with each of these dichotomies. And so if you were requiring the margin of the winning hypothesis to be selected, then you're going to decrease the VC dimension. You're going to prune away some choices of dichotomies associated with your function class, with your hypothesis. And that has the effect of reducing the VC dimension. And so this maximum margin criteria, this maximum margin idea, has the effect of decreasing your VC dimension because you're dealing with fewer models. And a smaller VC dimension means you can generalize better out of sample with a smaller number of input data points. Okay, so now we need a numerical way of measuring this idea of this margin. So we need a way to measure or compute the distance of a data point from the hyperplane. So let's introduce this notation, and we'll define xn. Xn is going to be some data point that's nearest the plane. Now, when we talk about this idea of nearest the plane, we need a definition for what the plane is, the hyperplane itself is. And so xn is going to be that data point that's nearest the plane. Some data point is going to be nearest, and let's call that xn. Now, the hyperplane consists of all of those data points x such that W transpose x equals to 0. That's exactly on the plane. So now we want to know what is the distance between this nearest point off the plane and the hyperplane. And that's what we're after. And once we get an expression for that, we can include that in our algorithm for finding the best hyperplane as some criterion that will favor solutions W that will prefer particular hyperplanes, i.e. W vectors, such that the margin is maximized, that gap between the data points, the nearest data points. So first we need to know what this distance is. How do we measure that? So let's make a lot of other assumptions, a couple of assumptions rather, for mathematical convenience. And one of them is that this W is going to be normalized. Now, of course, when we talked about the classifier, we said we get a +1 output when we have our score is greater than 0, or sine W transpose X, right? And so sine returns a +1 if W transpose X is greater than 0. It returns a -1 if W transpose X, our score, is less than 0. And so given that assumption, let's think about what a hyperplane is. Our hyperplane is our linear model W. Now certainly we can assume that W is going to be normalized so that W transpose X, when we talk about this plane, it points off the plane, Xn, W transpose X is going to be greater than 0, right? And we look at this magnitude because we don't care if this point nearest to the plane is on the positive side of the plane or the negative side of the plane. So what does this mean? Well, if I were to draw a hyperplane in 3 dimensions, right, this version of the hyperplane, so let's say I drew it like this sheet, and I'm just going to color it in just so you know and see better what that plane looks like. That version of the hyperplane, well, it's the same plane as if I drew it much smaller, right? And the only difference between the first version of the hyperplane and the second version of the hyperplane is to get from here to here, I just multiply by a scalar. So I might take this one, say multiply by 4, and I get this version of the hyperplane, but it's the same hyperplane. It doesn't matter what scalar I multiply it by. So in order to make things uniform and consistent, to have a well-principled way of measuring the distance of the hyperplane, I can certainly assume that I can scale it down and normalize it such that whenever I have a point off the plane, xn, that closest point, that W transpose xn is going to be greater than 0. I reserve W transpose x for any x input to be equal to 0, corresponding to points on the plane, but any point xn off the plane, my W transpose x, the magnitude of that is going to be greater than 0. Okay? So it doesn't matter what my W is. I can certainly scale it up and scale it down, multiplying by some scalar. It's the same hyperplane. So let's now take the following as a constraint. Now, if xn is off the plane, and it's the closest point by definition, the nearest point to the plane that's off the plane, I know that W transpose xn, I can scale up my W with a scalar up and down. It's the same plane. And I'm going to normalize it so that the score is going to be greater than 0 when it involves that particular closest off-plane point. I can also take it as a constraint that for the closest point, because I can scale this up, I can scale it up. Let's say it's like 0.001. I can multiply it by some scalar such that precisely for this closest off-plane point xn, that the magnitude of the score, W transpose xn, is exactly 1. So let's take this as a constraint. And I need this as a constraint because that closest off-plane point, that's exactly what I'm going to use to define the margin. And I need that closest off-plane point, the distance between the closest off-plane point and the plane, in order to measure the size of the margin, right? So to get that distance, I need this machinery. So here, I'm going to take it as a constraint that the magnitude of the score, W transpose X, where xn is the closest off-plane point, is precisely equal to 1, and I can do that by scaling up and scaling down this hyperplane. It's still the same plane, only I'm scaling it to make sure that this condition holds, this constraint where the closest off-plane point has the magnitude of the score equal precisely to 1. So now I'm going to do a little bit more fix-up. Remember, when we were talking about our weight vector W, we said it was augmented with some W naught, which we used to absorb the threshold because it was mathematically convenient when we talked about a linear classifier. So we're going to take this W naught and we're going to strip it out and go back to the original W that consisted only of the actual weights for the hyperplane. So we're going to remove this W naught, and now we're going to call this W naught our bias term, B. B stands for bias. So we're going to kind of undo that mathematical nicety that we had when we talked about the perceptron learning rule. So now, if we talk about the hyperplane itself, we said the hyperplane are those set of points x such that the score is exactly equal to 0. So what does that mean? It means that my W transpose x plus the bias, we no longer have an x naught. You could say the x naught is still there, but x naught was 1, plus the bias is exactly equal to 0. Okay, so that's the equivalent expression here, only we're removing the W naught term from my weight vector, and this is still my B times 1, which is effectively like your W naught times your X naught. Okay, so the plane itself is the set of points X such that W transpose X plus the bias is exactly equal to 0. And it's important to note here that we do not use X naught. X naught was just a times 1 dummy variable, but we're not using that. It's W transpose X plus B. That's how we define our plane. Okay, so let's now compute and come up with an expression for this measurement of the distance between this closest off-plane point and the plane itself. So xn is this off-plane point, and the plane itself is the collection of points x such that W transpose x plus B is precisely equal to 0. Now, of course, if you're on the plane, W transpose x plus B equals to 0. But if you're this point xn off the plane, W transpose x plus B, that magnitude, is precisely equal to 1. Okay? Now it's precisely equal to 1 because we know from this example, we can scale W up and down such that for that off-plane point xn, it's precisely equal to 1, that magnitude. Okay, so let's choose 2 points. We're going to call the first one x prime and the second one x double prime. And these 2 points are on the plane, right? So here's our hyperplane in 3 dimensions, so it's a sheet. Here's my x point on the plane and my x double prime on the plane. Now, because they're on the plane, they satisfy this equation, W transpose x plus bias is equal to 0. So that means to be on the plane, W transpose x prime plus B is equal to 0. And likewise, W transpose x double prime plus B is also equal to 0. Okay, so it just so happens that any 2 points define a line, and a line lies on the plane. And we set no restrictions as to which points this x and x double prime are. And therefore, when we say x and x double prime, that refers to any line that you can define collectively, which gives you a plane. Okay? So we have this x and x double prime lines on the plane, and we know they satisfy this expression. And so what we're going to do here in this treatment is we're going to demonstrate and prove that the weight vector W, which defines the plane, geometrically is perpendicular to the plane in the feature space, our x space. So we have these arbitrary points that satisfy W transpose x prime plus B equals 0. W transpose x double prime is also equal to 0, and that's the case because from our original definition, x and x double prime are on the plane. So because they both equal 0, we can equate these 2 expressions. And if we equate these 2 expressions together, we get W transpose x prime plus B is equal to W transpose x double prime plus B. Okay, because 0 equals 0, we can equate these 2 together. Interesting. So now we're going to subtract this expression, W transpose x double prime plus B, from both sides of equality. And we get a minus B on this side. B plus B minus B is 0. And we're left with a W transpose x prime minus W transpose x double prime is equal to 0. So we can factor out this common W here, this left multiplied by W transpose. And if we do that, that gives us this expression. W transpose times x prime minus x double prime is equal to 0. So if we look at this expression, well, we have W, all right? We have x minus x prime. What is x minus x prime? It's the line that connects x double prime to x prime. So there's that line. That's any line on the plane. Now, when we take the transpose of W, that W transpose here, this is a vector transpose, and this is a vector. So what we're doing here is we're taking this vector that connects x double prime to x prime, and we are taking the inner product between that and our weight vector. So again, we don't know at this juncture what our weight vector is. I'll put a question mark there. But we know that x prime minus x double prime is a line that's on the plane. Now, if I take the inner product between that W and a line that's on the plane, parallel to the plane, in order for that inner product to be 0, W has to be orthogonal to that line. Now, because that line is any line on the plane, that means by definition, W is orthogonal to the plane. Okay? All right. So now we've demonstrated that W is orthogonal, perpendicular to the hyperplane, right? So if you were to draw the hyperplane and you want to represent the W vector is orthogonal, perpendicular to the plane. Okay. So now we're going to take any point on the plane. We've now at this juncture demonstrated that W is orthogonal to the plane. We know that. So W is orthogonal to the plane. Let me draw that right angle box. Now, let's choose any point X that's on the plane. So if X is on the plane, X satisfies W transpose X plus B is equal to 0. Now, we're going to choose a point, and we'll imagine that this point is that place on the plane, that location, where our orthogonal W vector pierces the plane or comes in contact with the plane. Now, because W is orthogonal to the plane, W could be over here, right? It pierces the plane that X is there. If W is over here, pierces the plane here, X is going to be over here. So it doesn't matter where X is. What matters is that X is on the plane. Okay, so now we're going to choose a point Xn, which is the closest point off the plane. Now, as the closest point off the plane, what we want to do is figure out what that is, that distance that Xn, the closest point off the plane, what is the distance between it and the hyperplane? So how do we do that? Well, if this is my W vector, right, we know the direction of the W vector. What we need now is the projection of this closest point off the plane to this W vector. And that distance, that projection, is going to be the distance between Xn off the plane and the hyperplane. Okay, so we need then not the magnitude of W, we need the unit vector in the direction of W. We already know that W is orthogonal to the hyperplane, but we need the unit vector W because all we care about is that component of this off-plane point in the direction of W, which is orthogonal to the hyperplane. So how do you get the magnitude, how do you get the direction or the unit vector for a vector? You divide that vector by its magnitude. So W hat, the unit vector in the direction of W, is going to be W over its magnitude. So now if we measure the distance, we're taking the inner product between the unit vector in the direction of W and this distance, this vector that we draw between that point on the plane where W pierces the plane and that off-plane point, right? So here we write Xn minus X, that's this vector, and that vector goes from that point off the plane where W pierces the plane to that nearest off-plane point. So this on-plane point where W pierces the plane to that nearest off-plane point Xn. Now that difference, Xn minus X, that's exactly this vector. Okay, so to get the distance of that off-plane point to the hyperplane, we would just take the projection of this is a vector, right? Projection of that vector here onto the unit vector in the direction of W. Okay, and that's exactly W hat transpose times that quantity Xn minus x. Okay, so you take the absolute value of this because you don't really care if xn is on the positive side of the plane. Xn could also be on the negative side of the plane. So in that regard, you'd have w going in this direction. Here's x. You draw this vector. That would be xn minus x, and that would be a vector. I'll just draw a vector symbol. And now your projection would be in this direction, and that would be this distance. Okay? And so we care about the magnitude, but not whether it's in the positive direction or the negative direction. So we take the absolute value. Okay. So now, all right, well, let's substitute for what this w hat is, this unit vector in the direction of w. It's exactly this expression. So if we make that substitution, all right, well, the magnitude, the absolute value of the magnitude of w, that's just the magnitude of w. So if we started out with this expression, we substitute for w hat, the unit vector, w over the magnitude of w, transpose, so it's the transpose of this whole thing, times xn minus x. Okay, so this magnitude comes out, so that's 1 over the magnitude of w times, and then we distribute that w transpose to the terms in this parenthesized expression. Absolute value of w transpose xn minus w transpose x. Okay, inside the absolute value. Because the absolute value of magnitude is always positive, so you can bring that outside of the absolute value because its value does not change. So we have this expression for the distance between the closest off-plane point xn and that point xn on plane where w, orthogonal vector, pierces that plane. So now what we can do, we can take this expression inside the absolute value and we can add 0 to it. One way to add 0 to it is to add positive b, bias, and negative b. We collect terms and we get the following expression. So we put the positives with the positives, and that would be w transpose xn plus b. And we put the negatives with the negatives, minus w transpose x minus b. Okay, so now we notice that we have two terms here. We have w transpose xn plus b, and then we have this term, which is the same as saying minus of w transpose x plus b. And remember, xn was off the plane, and x is on the plane. That's important to remember. So as an on-plane point, we said it's a point that satisfies w transpose x plus b is equal to 0. So this term goes to 0, all right? And we also said that our w transpose xn plus b, we can scale it up and scale it down using that constraint where w transpose xn plus b is exactly equal to 1. We can scale it up and scale it down, normalizing this w, okay? So we replace this term with a 1 by our definition, and we're left with this expression, 1 over the magnitude w. So this 1 over the magnitude of w is our expression for the distance between that closest off-plane point and the hyperplane. Okay, so now our optimization problem becomes the following. So we want to find some weight vector w such that we maximize the margin. We want to maximize the distance between the hyperplane and the closest off-plane point. So we want to choose our w such that we prefer that plane that maximizes the distance between it and the closest off-plane point. Okay, and this is going to prune, as we said, the dichotomies that we consider and thus decrease the VC dimension. Now, it's going to be constrained optimization because we want to make sure where you can certainly scale up and scale down W, And as we're trying to find the W that maximizes this expression, we want to make sure that we're also obeying this constraint. And that constraint says, okay, while you're scaling up and scaling down to maximize this 1 over magnitude W, I also want to make sure that we're choosing a W such that we're tuning it so that for the minimum distance point to that plane, W transpose xn plus b is precisely equal to 1. Okay? So one observation also to make that you'll notice is that when we have this constraint, it's a minimization, okay, but we have equals to 1. It's a little bit messy to implement this minimization, this constraint. But one observation that we'll make is that when we have this magnitude W transpose xn off plane point plus b is equal to 1, that's the same as saying, okay, well, if you're off plane, your label is either plus 1 or minus 1, right? And if it's exactly equal to 1, because we're taking the magnitude, this is the score. And we're saying we want the score associated with this nearest off-plane point, nearest off-plane point. We want the score to be exactly 1, either plus 1 or minus 1. And through the absolute value, it's exactly equal to 1. So what does this mean? Well, if this point, ground truth, is a positive example, this score, the magnitude, it'll be positive 1, and we take the magnitude, and that'll be 1. If this point is a negative example, its score will be minus 1. And so what does this mean? If we take this expression, and this expression is a positive 1, and the ground truth label is positive 1, then we multiply the score times the label, and it's going to be positive. If it's a negative example, this score, W transpose xn plus b for this off-plane point, so it's on the minus side of the plane, the score is going to be minus 1. If we multiply that minus 1 score with a class label, yi, that's also minus 1, it's also going to be positive. So this idea of the magnitude W transpose xn plus b being equal to 1 is the same as taking your class label and multiplying it by the score without the absolute value. So what does this say? It says we can now express this equivalent optimization problem with this constraint that has this minimization of W transpose xn plus b is equal to 1, instead of saying the smallest point or the point closest in distance to the hyperplane, we can now get rid of this constraint or find an equivalent expression that gives you the same result. So now, instead of a maximization problem, if we took the reciprocal of this magnitude of W, that would be the same as minimizing 1/2 W transpose W. Because if we set the gradient equal to 0, what do we get? Well, we get a leading 2 that goes away, and we're talking about W, right? So here, this maximization problem of 1 over the magnitude is the same as 1/2 W transpose W. So if we take the reciprocal for the objective, that's the same as minimizing the reciprocal. So maximization of one quantity is the same as minimizing the reciprocal. Okay. So if we said find the x that maximizes 1 over x, it would want to make x small, right? Because that's going to maximize. If we took the reciprocal, right, 1 over x, that's x, now we want to change that to a minimization problem. And again, we want to make that small. So it's the same problem. Okay, so we put those two together, and so now we minimize 1/2 W transpose W. It's a minimization because it's the reciprocal of this objective. And then our constraint here, we make use of this fact, and we have yn, so the class label for xn, times the score. So this is the label times the score. And it's greater than equal to 1. It's precisely equal to 1 because here in this minimization problem, the solution is going to be the closest point, right? So we want the score, the magnitude of the score for the closest off-plane point to be equal to 1, right? And so any point that's further away from the plane, so if you have the plane here and you have the margin here, if you have the closest off-plane point xn, and it's right here, that defines the margin. So that means if W transpose xn plus b is equal to 1, well, any point, let's call that xj, that is further away, well, its score is going to be larger. So the magnitude of its score is certainly going to be greater than 1. Okay? So we can eliminate this min issue for the magnitude of the score for the closest, for the off-plane point. And this idea of closest is expressed here using this inequality. And we can just completely find the equivalent expression to say the closest point is the one that is at least equal to 1. Okay, so now this changes our optimization problem to minimizing this objective, i.e. the distance from the margin, subject to getting the classifications right, meaning that the closest point off plane on the positive side, i.e. agrees with its score, its label agrees with its score, or the closest point, at the same time the closest point on the minus side, to the closest point to the plane on the minus side of the plane coincides with its score. And the only way to make this equal to 1 is if the label equals the score. Because if the score is equal to 1, plus 1, and the label is equal to plus 1, well, it's getting classification right. If the score is equal to minus 1 at the same time the label is minus 1, it's getting classification right. So what this now says is find the maximum margin, 1/2 W transpose W, subject to getting the classifications correct. Okay? All right. So the L2 norm is cumbersome. So we convert this to an equivalent optimization problem, and the nearest point on the margin that has the smallest value. That's why we have this minimization. We're trying to find an off-plane point, but we want to find that off-plane point who's closest to the plane, and that's going to be W transpose xn plus b is equal to 1. So we find the equivalent minimization here for this constraint by just observing the fact that we can scale the score up and down by scaling the hyperplane up and down. It's the same plane, such that the closest off-plane point has a score that's exactly equal to 1. If that's the case, then any off-plane point that's not the closest is going to have a score greater than 1. And so we use this inequality to give us the same solution as this minimization in the original constraint. Okay. So let's look at the SVM formulation. And this is to minimize the distance, or rather to find the maximum margin. So the hyperplane that has the maximum margin. So let's take a look. Let's take a look at the SVM formulation. So, let's take a look at the SVM formulation. So we have a constrained optimization problem where our objective is to find the hyperplane W that maximizes the margin. And that is the distance between the closest off-plane point and the hyperplane, while at the same time getting the classification correct. And what that means is that for each point xn, the class label agrees with the normalized score. normalized score. And if we use this greater than equal to, it's going to prefer hyperplane's W such that the closest point, who scores exactly 1, has the classification correct. Okay. Now, the W is drawn from D dimensions, so it's has a D-dimensional model, and our bias is also drawn from the set of reals. Okay. So now we have inequality constraints, and we want to make our lives easier with this optimization, and we're going to use a technique to turn these inequality constraints into equality constraints. And the reason why we want to do that is because when we have inequality constraints, when we say, for example, maximize a function, here's some function f of x, here's my x, and here's some constraint, right? Let's say that's going to be a value x prime. So if we said maximize this function f of x such that x is less than x prime, now we have to check all of these values less than x prime. That's a lot of checking. If we said maximize f of x, here's my f of x, subject to an equality constraint, here's x, equals x prime, well, I only have to check one condition, right? And that's my solution. So it's always easier in an optimization to have equality constraints. And so next time, when we meet on Tuesday, we will look at some very powerful methods, Lagrangian optimization, to find the equivalent optimization problem with an equality constraint rather than this inequality constraint. Stay tuned. We will finish there, and we will talk about this further on Tuesday. Stay healthy, stay safe, and I will see you both on Tuesday.